Well, for the most part, we are kind of done learning how to find the antiderivatives. You've got your rules, basically just the plain ones are pretty straightforward. And then you've got substitution, and if that's not an option, you've got integration by parts. Remember, that's kind of your last resort. A change in your position is called, does anybody know, possibly from physics? Displacement. And that could be anything. It could be you in your car. It could be, a lot of times they refer to particles, as you can see in this one here. Or it could be a bug, who knows. But displacement is the change in position. So that function that you have down there says ds over dt. Remember, s is kind of position. Describes the velocity of a particle moving along the s-axis for a particular time. It says if the initial position is 9 centimeters, determine each of the following. So ds dt. So if you had s of t, some function, that's position, correct? So how is it we always got to that velocity one? What did you have to do? Take the derivative to get down there, right? And what would you have to do to get back there? Antiderivative. You see how they work together? It's a big circle. And let's not forget there is another option. Down here would be acceleration. But again, to get back, same idea. Well, I believe on mine, do I have the graph on mine? I don't remember. There it is. Why don't we go ahead and you can grab a graphing calculator if you want, and let's get that graphed. T squared minus all that stuff. And let's try and get our window to say something similar to that. All right, now that everybody's got a graphing calculator, let's go ahead and we'll do t squared minus 8 over t plus 1 squared and see what happens. Do I have to worry about my mode, like radians, degrees, or anything like that for this one? No, there's no trig involved, so it doesn't really matter. And so y equals, well, we don't want that. Let's get that out of there. You can just use x. You don't have to get it to try and say t. Minus 8 divided by. I'm one that's normally extra careful on the dividing by ones. I always put as many parentheses as I can. That's going to be the parenthesis for the entire bottom. And then I'm going to put another parenthesis for the x plus 1. Because now I can use the caret key, or actually we don't have to on this one, we can just hit squared, and then I can close off the other one as well. The key is that x plus 1 has parentheses around it to square it, but then you also have to put parentheses around that so that you make sure you divide by all of it, okay, instead of doing all that and then squaring. This one you should be all right without the extra ones, but I'm always extremely careful. If I were you, I'd probably change the window, because you can see what I gave you back there. You'd probably have your x go from 0 to 5. Right? Because that's kind of where I told you to graph on there. Of course, depending on the problem, you might graph it somewhere else, depending on what you need to do. But window. So let's just make that 0 to 5. And x scale 1, does that make sense? Each tick mark being 1? Yeah, that's probably all right, right? And what do I got there? I had you going from negative 10 to 30. So will this graph be somewhat distorted? Yeah. And what I would do is, instead of my x scale being 1, that's just going to put a lot of little marks on there. Well, what is mine? Mine's kind of 10. Is that okay to make your x scale 10? Is that too big, too small? It's fine. You could have even done 5 if you wanted to. And of course, you got to do what is familiar to you. So what is it there that I just graphed? It says ds dt on your notes. So that's their velocity, correct? And the question then says, let's determine when the particle is moving to the left, right, and stopped. So we're going to say that moving to the right is our forward, or our positive. And we will say moving to the left is our then negative. And of course, stopped is when it is 0. Well, we're at 0. There's many ways to solve that, but does anybody remember one of those little tricks that we did earlier this year? Yeah, go to calculate, right? This thing can do a lot for you, right? So calculate. What do I want? To calculate a particular value? Yeah, calculate the 0. Very good. Because this isn't the position graph. This isn't telling me where it is. This is telling me the velocity of it. And a velocity of 0 means that the object, whatever it is, has stopped. So we'll do that, calculate the 0. Does that look like a good left bound? That's horrible. And so you work your way back. There's a slight delay, so I have to be careful not to go too far. Does that look like an all right left bound? At least it's left of the spot, right? Could you go a little further if you wanted to? Sure. Left bound. Oh, right bound. Well, better get to the right of the point. Yeah, because we're looking for the 0, right? That's where we want to know when it equals 0. My guess, really, you could just get closer if you want, but it really doesn't matter. That looks good. So I would say, because the question A says, determine when the particle is moving to left, right, and stopped. Well, it is stopped at approximately 1.25. Should we just say 1.25? Just to do that. So approximately 1.25. Yeah, I believe it says seconds in the problem, doesn't it? Well, it doesn't, but we'll say that it is for this one. So stopped. And that is not the one. So stopped, answer, approximately 1.25. And we'll say seconds. It could actually be hours, who knows, but we'll say seconds. So how about to the left or to the right? Well, let's go back to the graph and find out. Where is this thing heading left? Or in other words, negative. Where is it negative? Okay, what we're saying here is to use interval notation. You can definitely do that. It's just saying for us to look from, based on our graph, from 0 to 5, but look up at the interval that I gave you. Are you supposed to include 0 based on the original problem? Yeah, if you look right here, I am asking you to include both values, correct? And at 0, is it going left based on our graph? At 0, is it going left? Yeah, because it's negative. Because you take a look at our graph. Well, you can't really see it. But at 0, at a time of 0, it's negative. And it's negative all the way up to that approximately 1.25, right? So you could do interval notation if you wanted to. Or you could just do it many other ways. For example, moving to the left, you could say, as I was being told, 0, comma, approximately 1.25. And based on our answer, should we put a bracket on that or a parenthesis based on the way we're kind of answering things? Probably parentheses because we're not going to include that one because it stopped at that one. That'd be fine. Or some people like to do it this way. It's the same thing, though. This one is moving left. And moving right, then, wherever it happens to be positive, which would be approximately 1.25, comma, 5, and then bracket. Because at 5, it is still moving to the right. Do we know what happens after that? No, we don't. But we don't know. All I'm asking you here is from 0 to 5. That's all the question asked about. And that's why we only graphed that much. Or again, you could have done approximately 1.25. And let's see. Whoops. Like that. Either way is fine. Right. Parentheses means it's not included. Bracket means it is, for those that want to use interval notation. Questions? What is the particle's position at time equals 1 and time equals 5 is letter B. Well, particle's position. Let's go back to that first one. Which one of these actually tells you position? Is it S of t, V of t, or A of t? Which one do we have right now? We have V of t. So if I want to get to position, because this is velocity, because it's the change in position with respect to time, which means it's that one. I want position, which means I have to take the antiderivative. Well, let's take the antiderivative. Where did we start with this thing? Well, we started at 0, correct? That's the time I told you to start at, from 0 to 1 of t squared minus 8 over, the 1 came from right there. If I calculate this, this will calculate displacement, how much it moved. Okay, if you do the antiderivative, it will tell you how much it moved. Okay. We're going to have to do them separately. Yeah, now you know how to do this in your calculator. So why don't you go ahead, and actually you taught me how to do the one where you can just enter the value, which is really nice. Go ahead and find that. And plus, we already have a graph, right? We've already got it right there. It's sitting right there. So calculate. Calculate what? Number 7? You said you can just type it in, so 0. Enter. 1. Enter. Does it make sense that it's negative? Why does it make sense that it's negative? Yeah, it's moving to the left, and this area is underneath the x-axis. So remember all those rectangles we were making way earlier? Wouldn't the rectangle be going down? So when you took the width times the height, it would be negative. So unfortunately, negative 3 and 2/3, I think we all recognize that, correct? This equals negative 3 and 2/3. That is displacement. That is how much it has moved. If that's how much it has moved, is that its position? That is how much it moved from 0 second to 1 second. Where was it originally? Nine centimeters. From that 9 centimeters, it has moved left 3 and 2/3 centimeters. So where actually is it? Basically, just take the original plus 9, and you get where it is, which is 5 1/3 centimeters. Once again, taking the antiderivative is displacement, or how much it moved. Why don't you try and figure out the particle's position at 5 seconds? You could do it either way. You can go from 1 to 5 and use 5 1/3 as your starting spot, or just go 0 to 5 and use what as your starting spot? If you go 0 to 5, you're going to use 9 as your starting spot. Either way should work. You try that one now.